This is the last topic of this section, rational powers of differentiable functions. And in this next result, we are going to extend the power rule for differentiation, which we already know, from integer exponents to rational exponents. That means here now n will be a rational number, and this is the actual statement. And in fact, it is also called so power rule for rational powers. That means a power where the exponent n is a rational number. So let's see the statement. If n is a rational number, then this function x to the power n is differentiable at every interior point x of what? Of the domain of the power x to the power n minus 1, the previous lower power. And the derivative of this function at such a point x has this same form that we have seen before. That is, it is n times x to the power n minus 1. Note also that we want this x to be an interior point of the domain of x to the power n minus 1 because this is our answer as the derivative. So we want x to the power n minus 1 to be a real number. That is, at that value of x, this n minus 1th power of x should exist. Now let's see how it can be proved using implicit differentiation. So we start the proof with the fact that n is a rational number. Since n is rational, there exist integers p and q with q greater than 0 such that n is equal to p divided by q, because this is the definition of a rational number. And now we name the function also. That the function of course is x to the power n. We give a name to the dependent variable, say y. Then that is equal to x to the power p divided by q. Now if you take the qth power on both sides of this equation, then you get y to the power q equal to x to the power p. Now by that theorem from advanced calculus, y is differentiable as a function of x. Which theorem? How did we begin the section? We began the section by considering some equations, and we wanted to differentiate both sides of those equations with respect to x, treating y, those equations involved x and y, treating y as a differentiable function of x. And that is how the process of implicit differentiation was explained. But that raised the question of whether y really is a differentiable function of x. And to answer that, a theorem was mentioned from advanced calculus, which is this, that if your equation involving x and y takes this form, which is the most general form, f of x comma y, which is some expression involving x and y, that is equal to 0. And there are some conditions on the function f itself, that f is continuous, its partial derivatives with respect to x and y are themselves continuous, and the partial derivative with respect to y is non-zero, then y is a function of x. That's the first thing. Then y is a function of x, although it will be hidden in this implicit relation. And moreover, y will be a differentiable function of x. In this case, our f is this, y to the power q minus x to the power p. It is a polynomial function in x and y in two variables, so it is continuous. But we do not have to worry about these conditions. The authors say that these conditions are automatically true for us here, and anyway we don't really know what continuity of a function of two variables even means. So we are going to assume that this is true in this case, and that is why y is a differentiable function of x, and that will now allow us to differentiate both sides of this equation with respect to x, treating y as a differentiable function of x because of this theorem. And that is just implicit differentiation, and from there we will be able to find dy dx. So differentiating both sides of this equation with respect to x implicitly, of course, we get this. To differentiate the left hand side, we have to use the chain rule. Now the ordinary power rule here is applicable because cube is an integer, and for integer exponents we already have the power rule. So it assumes this form, the derivative q times y to the power q minus 1, where you are applying the power rule to differentiate the outer room, which is the qth power room, keeping the inner room y intact, and then you multiply that by the derivative of the inner room with respect to x, that is dy dx. And the right hand side also, here also p is an integer, so the derivative is just p times x to the power p minus 1. Now from here we will find dy dx. So assuming y to be non-zero, we next have this. The question is, can we make this assumption? Yes, we can make this assumption, because what is y? Y is x to the power p divided by q. If we avoid the input x equal to 0, then y is never going to be 0. So with that assumption, we can divide both sides by q times y to the power q minus 1. And if you do so, this is what we get. Dy dx equals p divided by q times, this was, here the exponent was q minus 1. If when you transfer that to this side, it will be 1 minus q, because it will be negative of q minus 1 times x to the power p minus 1. Now you write what y actually is, x to the power p divided by q whole to the power 1 minus q times x to the power p minus 1. You know from one of the rules of exponents that the exponents get multiplied in such a situation. If you have iterated exponent on top of that you have exponent. So p over q times 1 minus q times this. Now if you do the multiplication here, you will get p divided by q minus, after cancelling q you are left with p, and then you use that other rule of exponents, where if you have something like this, a product where the bases are the same, then you add the exponents, p divided by q minus p and p minus 1. After cancelling minus p and plus p, you have p over q minus 1, which is just n minus 1. And along the way you also note that p divided by q is n. So that's how you have got what you wanted to get. And here also you see that even when the exponent n is rational, the form of the derivative is still the same, n times x to the power n minus 1. So you next see example 6, which has two parts. This is part A. We are again differentiating the square root function, square root of x. You know that this function is defined on the set of non-negative real numbers, that means 0 is included. And we actually already know that the derivative is 1 divided by 2 times square root of x. But let us now do it using this formula. Now we can use it because our exponent is a rational number, 1 divided by 2. So by this formula, the derivative is 1 divided by 2 times x to the power n minus 1, which is minus 1 over 2, and that is 1 divided by root x. And that's how you get your original formula back. Note that this makes sense only when x is a positive real number. Now you cannot take x equal to 0. And that matches with what the statement of this result says. You recall that x should be an interior point in the domain of x to the power n minus 1. In this case, x to the power n minus 1 is this. That means 1 divided by root x, and its domain is the set of all positive real numbers. Okay, so from there only, if you choose an x, there you can have the derivative. If you take x equal to 0, then this does not work. Now using this new law for differentiating rational powers, we can differentiate other rational powers as well, not just the one that we already know. For example, ddx of x to the power 1 divided by 5 will be, by that formula, 1 over 5 times x to the power 1 over 5 minus 1, or in other words, 1 over 5 times x to the power minus 4 over 5. Note that the original function has the entire set of real numbers as its domain. This one, however, is the set of real numbers but from which 0 has been removed. Now we can next also combine the new power rule with the chain rule like this. If n is a rational number and u of x is a differentiable function of x and u of x to the power n minus 1 is defined for some value of x, then u of x to the power n is also differentiable at that value x and its derivative is given by this. You can understand how that happens, right? This is differentiable and that comes from the chain rule itself. U to the power n is differentiable and its derivative is obtained by applying the chain rule. First you differentiate the outer nth power room, assuming that u is a differentiable function of x. In fact, that is given right here, u is a differentiable function of x, and you obtain this derivative, and that itself you can do because now you have power rule for differentiation where the exponent is a rational number and the derivative of the outer room is n times u to the power n minus 1, and then to complete the application of the chain rule you have to multiply this by the derivative of the inner room, which is u with respect to x. And now let's also see how this can be applied in some examples. So we see example 7, where say the function to be differentiated is this 1 minus x square to the power 1 divided by 4. Think of 1 minus x square as your differentiable function of x u, and this is the nth power of 1 minus x square, where n is 1 divided by 4, the rational number. So you are differentiating u to the power n, and by this rule first you apply your power rule with the rational exponent 1 divided by 4. So you get 1 over 4 times 1 minus x square to the power 1 over 4 minus 1, and then you multiply that with the derivative of u with respect to x, and this one of course is minus 2x, and then after a little simplification this is your derivative minus x divided by 2 times the 3/4 power, perhaps I should not say it like that, 1 minus x square to the power 3 over 4. Note carefully that the domain of the original function u to the power n is this closed interval minus 1 comma 1, but now the domain of this is the open interval minus 1 comma 1. You can no longer put x equal to 1 or minus 1. If you do, this will become meaningless. And finally we have part B, where we are differentiating cos x to the power minus 1 divided by 5, again of the form u to the power n, where n is the rational number minus 1 divided by 5, and u is this function of x cosine function, which is a differentiable function of course. But at the same time note that for this entire function u to the power n to be defined, cos x should not be equal to 0 because we have negative exponent here. So actually this is just the reciprocal of cos x to the power 1 divided by 5. Now what are the real numbers x where cos x becomes 0? These are the odd integer multiples of pi divided by 2. So those x values are excluded. Anywhere else, if you take any other x, then you can differentiate this function at that x. And you just think of it. What are the odd integer multiples of pi over 2? They form a set which if you remove from the set of real numbers, then you are left with some intervals. So from that collection of intervals, if you take any point, then that point will be an interior point because there is no boundary. And that is why at any real number x which is not an odd integer multiple of pi over 2, you can differentiate this function. And by our formula, this is the exponent times cos x to the power the exponent minus 1 times the derivative of cos x with respect to x. Now this becomes minus 6 divided by 5, and ddx of cos x is minus sin x. After simplification you get this. Okay, so here also those x values are excluded which are odd integer multiples of pi divided by 2. Elsewhere this makes sense.